All right, hi everyone, and today we're super excited to host Dr. George Pavlakos, who is currently a postdoctoral researcher at UC Berkeley, advised by Anju Kanazawa and Jitendra Malik. Dr. Pavlakos' research interests are computer vision, machine learning, and robotics. Previously, his PhD dissertation received the Morris and Dorothy Rubinoff Award of the Best Computer Science Dissertation at the University of Pennsylvania, advised by Dr. Kostas Danielidis. He is an area chair for this year's CVPR and outstanding reviewer for ICCV and 3DV last year. And he has also spent time at the Max Planck Institute with Michael Black and at the Facebook Reality Labs. Without further ado, let's just welcome George.
Thank you very much, William, for the introduction, and thank you for inviting me and having me here. I'm very excited to be giving a talk today. Hello, everyone. My name is Georgios Pavlakos. I'm a postdoc at UC Berkeley, working with Anju Kanazawa and Jitendra Malik. And today I would like to talk about our recent work on reconstructing and tracking 3D humans from video. This includes some recent work that I'm very excited about. If you have any questions, please don't hesitate to interrupt me. I'd be happy to go into more details about something. All right, so let's get started. Okay, so first things first, just to be on the same page, today the talk will focus very heavily on humans. Most of my work revolves around perceiving humans, which I consider to be a very fascinating subject. And from an applications viewpoint, humans are actually in the center of most of the visual content that we have access to: pictures, selfies, videos of people doing various activities, sports, TV series, movies, TV shows, all include and focus on humans. So being able to reconstruct and reason about humans is crucial under all these settings. Also, from a learning perspective, as humans, we learn about the world by watching ourselves acting on it, or by watching other humans interact in the world. So I believe that perceiving humans will be very crucial towards understanding human intelligence and building AI systems. And finally, from a computer vision perspective, I think it's a very fundamental problem, which includes many of the challenges we have in other settings, like dealing with dynamic objects, articulation, multiple humans, occlusions, tracking people, or looking at pose priors, motion priors, social interactions, clothing. So if we are able to solve all these problems, some of the techniques or the tools that we develop should also be applicable in other computer vision problems as well. So that's where I'm coming from. The other ingredient that I believe is crucial here is the ability not only to detect humans on the 2D image plane, but the ability to actually perceive humans in the 3D space. And I have a small example here that actually transcends humans. This is actually more about gods. So I'm originally from Greece, so I couldn't help it giving an example like that. So this is a recreation from the west pediment of Parthenon in Athens. And here you can see goddess Athena and god Poseidon fighting over who will be the patron of the city of Athens. And so when you see a scene like that, you don't perceive only the bounding boxes around the people. You don't look only at the 2D joints. You are actually able to make a mental 3D representation of the people involved here, which you can rotate in your mind and see it from different viewpoints. So this is how you perceive humans, and this is how we want our systems to also perceive humans. So when you go to 3D, let me actually switch that to something less distracting. So when you go to 3D, you make reasoning about relations between humans much easier. So here, Poseidon occludes Athena. This is easy to perceive in the 3D space. You can also have interactions with objects, and here Athena is holding her spear and her shield. Poseidon is holding his trident. The proximity is not just in 2D here, but it's actually in 3D. There is a contact. They are actually holding these objects. And then, of course, you have the rest of the world, which is also in 3D. So you can combine everything together very nicely in the full 3D scene. So that's how I'm thinking of this problem. But before we go there and perceive the whole scene, we want to be able to perceive humans in the first place. So this is a problem I have been working over the last few years. Given an image of a person as input, we want to get a 3D reconstruction of that person in the output. And the main dimension we have been pushing for quite some time was towards increasing the detail of the reconstruction. So early on, we started with just a very rough 3D skeleton of the person, just some 3D key points. And that's from quite a few years ago. Results look like that. Methods were working on this type of images or indoor environments. Not super interesting backgrounds, but at least it was, we got some fully automatic results. And then we made steps forward. We reconstructed the full body surface. Here, this is in the simple body model form. And with this approach, we're able to get very good results for 3D shape estimation and pretty smooth reconstructions overall. And then we pushed even further towards getting more details, like the face and the hands of the person. And this was in the form of the simplex model. And here you can see some more results from video. This is running on its frame separately. You can see some jitter here, but again, this is automatic, and we're still pushing towards improving results here. So yeah, that was the problem that I focused primarily. This is some work that I focused primarily during my PhD, 3D reconstruction of humans from single RGB images. And we did achieve some improvements, but there are still some failures in some of the cases that we care about. So this is what we get if we apply a state-of-the-art method on some movie data. And this is an interesting case, but it's also very challenging because you have heavily occluded, heavily truncated people. So you see only part of the body, and many of these methods were actually struggling here. But actually, we do care a lot about movies. We think that the data we can collect from movies is actually very interesting. And we can think of movies as a treasure trove of human behavior. And you want to be able to analyze this data so that you can understand human behavior, human interactions with the environment or with other people. And you can even study storytelling or study different cultures. So this is a very interesting use case for us. But the data, of course, as you can see here, is very, very hard. You have close-ups, you have heavy truncations, you have shot changes, B-rolls. There are many levels of complexity here. Yeah, so that's how some of the methods worked like a little while ago, and that's the type of results we want to reach to that point. So yes, this is part of the work that will appear in this VPR this year, human mesh recovery from multiple shots. So shot changes are very common in edited media like movies and TV series, and they are often treated as discontinuity in the video stream. And what happens is that we often treat each shot and process each shot independently. However, each shot only includes partial information about the scene. So in the case of humans, for example, if we treat each shot independently, we have to deal with challenging viewpoints and truncated bodies. And recent approaches for 3D human reconstruction perform well when most of the body is visible, but they do struggle in cases with heavy truncation. However, our insight here was that it is only the shots or the viewpoints that are actually discontinuous, not the underlying scene in itself. And what I mean with that is that we do know that the 3D pose should change smoothly across its sequence. So this means that each shot provides different viewpoints of the same underlying 3D scene. And its viewpoint can be treated as complementary information for the reconstruction. So the 3D scene remains the same. It's only the viewpoint that is different here, particularly at the south boundary. So effectively, our key insight was to integrate information from these otherwise independent shots, which allows us to improve the overall quality of the 3D reconstruction. So we take information from both the images before and after the shot change to recover a more accurate 3D reconstruction. So that's the overall pipeline that will follow here. First, we assume we are given some tracklets for each person. Then we apply some optimization approach to reconstruct the bodies before and after the shot change. And then after applying this technique over multiple movies, we use the reconstructed 3D results as training data with pseudo-ground truth for training downstream models. So let me start with this second step, this multi-shot optimization. And before I go into more details here, let me also do a short introduction to the simple body model. So this is what we'll use for most of the presentation today. So simple is a vertex-based model that makes a convenient decomposition between the pose, the 3D configuration of the body, and shape, the identity of the subject, how tall, short, or thin a person is. And for the model, we first define a skeletal rig, which is effectively kinematic tree, and we also have a template mesh on the right. So regarding the shape parameterization here, we have a set of shape parameters beta, which are coefficients of a PCA shape space. And so for the shape space here, Sn are the eigenshapes, and BS is the deformation based on the shape of the person. And you can see how the template changes based on this shape-specific deformation. And independently of shape, Simple also defines the pose represented by theta, which includes the 3D rotation of its body part with respect to its parent in the kinematic tree. So with this information, we can deform the skeleton of the body according to the pose parameters. And our goal is to also deform the mesh accordingly. And Simple uses linear blend skinning for that. And with LBS, the location of its vertex depends linearly on the location of a specific set of joints. So this LBS function deforms the identity template based on the pose, giving us an output mesh of roughly 7,000 vertices. So that's about the model, how we model the human body. The next step is to effectively be able to reconstruct this body or recover the parameters of this model given an input image. And here we use this simplify or simplify X paradigm, where first we detect some key points on the image. These can be detected with these are 2D key points detected with some out-of-the-box software like OpenPose. And then we fit the model to this key point detection. So we want to recover the parameters such that the projection of the mesh agrees with these 2D key points. So for this model fitting step, we pose an optimization problem, and we define an objective function that we want to minimize at test time. And here we have a data term, which is based on joints projection. And effectively, we want to find a 3D pose here that, when projected to the 2D image, agrees with the detected 2D key points. And we also, I mean, this is definitely necessary here, but this is not enough. We also have some prior information about the human body, or how it should deform, like what are valid poses, what are valid shapes. So we encode all these prior knowledge we have about the bodies, about the human bodies, into these prior terms, which can be related to pose, shape, expression, or avoiding interpenetration. So all these are captured under these regularization terms. And so what happens here is that at test time we have this objective, and we minimize it using an iterative optimization approach. And you can see what happens at test time. So we start from the mean pose and then gradually align the model such that the projection agrees with these 2D detections here. And we can recover the 3D shape. So that's a more general technique that we have developed before. Of course, this is also applicable here. Like we can use this reconstruction, like this optimization method, to align the body model to 2D key points for each image for the frame before and after the shot change. The crucial thing that we have here is that we know that these poses should be roughly the same, or they should agree as much as possible. So we can apply some 3D consistency for the 2 poses. For the important thing, though, is that this consistency shouldn't be applied on the camera frame, because the camera viewpoint changes abruptly during, before and after the shot change. So instead, what we do is to apply the 3D consistency on the canonical frame. So what happens is that the human is at the center of our world, and we want its pose to be consistent before and after the shot change. And the cameras are recovered recovered jointly with this optimization. So while we optimize for the pose before and after the shot change, we also optimize for the 2 cameras before and after this transition. So we get this global. We are, I mean, by bringing the human at the center of the world, we are able to optimize to enforce this 3D consistency constraint. And I just would like to also highlight that recovering these camera locations here using some more traditional approaches like structure from motion would be very hard, exactly because we have very little or potentially very little overlap between the background here in the first and the second frame. So this recovery is of the cameras as well is feasible exactly because we are doing this this human-centric optimization. So here you can see some results and some comparisons with previous approaches. This is our result. It's quite smooth. Previous approaches fail, sometimes very badly, because of these heavy truncations that happen in the images. And yeah, the nice thing that this is an automatic approach. We can apply it in large scale over many hours of movie data. We apply this on AVA, and we collect a lot of these 3D reconstructions over many movies. And what we do with that is that we treat these 3D reconstructions as pseudo-ground truth. So because we have information before and after the shot change, we effectively have this form of multi-view information, which makes the recovery much more, the pose and shape recovery much more reliable. So we can use this data as training data for to supervise models for direct image to 3D inference. So that's the next step, and that's the data that I was showing also earlier. Yeah, there are models. I mean, here I won't go into too many details here about these direct prediction models, but I will briefly make a description because those will be relevant also later in the presentation. So we do have these models that allow us to go directly with, in single shot inference from an image to full 3D for the person here. And we can do this from a single image, and this is the HMR or Human Mesh Recovery network, or we can do this also over video. And this is the we use transformer architecture here, but effectively this is a model for human mesh and motion recovery. That's how we treat this reconstruction here. And yeah, we use the data we have recovered to train these downstream models and make direct inference of 3D poses from images or video. So for some of the results here, first I have some examples where we highlight the importance of having multiple views or this multi-shot information. So if you consider only one frame, either before or after the shot change, you might have bad reconstructions depending on the visibility. You can do much better if you have frames before and after the shot change. We saw also results for these direct prediction models, and here we compare with previous approaches that often fail because exactly because we have this heavy truncation here. We have some more examples, and the nice thing is that the models we train are actually quite generic, so they are more robust than what we got before. So we can even apply this in other settings. This is not like specific to movies. We can also apply it to this. This is from this vlog dataset where people record these visual diaries, and here we also get improvements compared to previous methods. Have some more results from different viewpoints as well to appreciate the 3D reconstruction, the 3D nature of the results. And I also have some failures here. I want to highlight that this data can indeed be super challenging. So it's possible that you see very little of the human body, maybe less than 5% visibility. And here is where this reconstruction is actually failing. We have observed that these viewpoints, which are actually happen in movie data, but because of the visibility, we do get very bad reconstructions here. So this is a point for improvement in the future. And I also have some comparisons with the temporal model. The previous works on the top right and bottom left have problems. Our method is performing better here, is more robust and smooth. Yeah, we'll keep this playing, but if there's any question, that's a good time to interrupt me because I'm going to switch gears soon. Okay, so yeah, that's our work on this human mesh recovery from multiple shots, and that's our overall pipeline here. One thing that I didn't emphasize enough, though, here is this first part of the pipeline, like getting this tracking of identities, and I kind of push this under the rug a little bit, but this is a very important part of the method, because if we have this identity tracking working automatically very well on this type of data, we should be able to deploy our method on any potential movie here. So yeah, I'm very interested in this aspect as well, and this is I will present also work that we have developed to address this part of tracking people in video tracking, and this is a work that will appear in CVPR this year. So tracking people by predicting their 3D appearance, location, and pose. We call our approach PHALP, tracking by prediction of human appearance, location, and pose. And this is an approach that the goal was to be able to track people, to track identities in video, and make this as robust as possible. So one of the goals was actually to make this work in the wild video. So for sports, we wanted also these typical pedestrian detection data sets, or this can also be applicable in movies. So we wanted this robustness for the method and this applicability in diverse settings. However, I mean, we developed this, like one of the reasons we developed this approach was because we were looking at the literature, and most of the related methods for person tracking were actually focusing on this pedestrian detection setting, making them not so applicable for different scenarios. And the other important thing is that they also track people almost exclusively on the 2D domain. So they track bounding boxes, they track silhouettes or 2D key points. So this is one of the this is what we consider to be a limitation of these methods, and I will try to explain why, or like why our understanding of why that's the case, why people focus so much on these 2D tracking methods. So I think first of all, this is type of a legacy issue because of the datasets that were used traditionally for this problem. So the application setting here was often surveillance, where we had these low resolution videos. People were far away. We could see only part of the person. Maybe we couldn't see the face, or we could see like roughly only the color of the clothing. Here, however, this is not the case anymore. So this is how the data, our data, look like today. We have high resolution cameras. We have our cell phones that we carry all day. We might go to SF during the weekend and ride a bike and record our friends. So we want to be able to process this kind of video, or this kind of video, you know, from sports, where we might record a basketball game, or even this gym class. So these are the settings that we care about today, among others, of course. So there is no reason to constrain ourselves only to surveillance here. So that was one of the reasons why the data sets that were available were one of the reasons that we have been focusing so much on 2D tracking here. The other reason we believe is that has to do with the methods for lifting people to 3D, which were not very reliable, at least until 5 years ago. So, you know, maybe 20 years ago, we could reconstruct these Maybridge sequences, but we couldn't go too much beyond that. So this is not the case anymore. Today, we particularly following this human mesh recovery approach and the follow-ups, we do have very robust and reliable methods to reconstruct, to lift people to 3D from 2D images. And we can even do this from very challenging video, like movies. So we can reconstruct people from pixels. And the question becomes whether this is useful, or this can be useful for tracking. And we argue that yes, this it's important to actually be able to use 3D information for tracking. And the first insight, or the first reason, has to do with occlusion. So occlusion is probably one of the hardest problems when it comes to the tracking setting, because occlusion on the 2D space is hard to disambiguate. So it's hard to say, almost impossible to say which person is closer and which person is further away here, because they overlap on the 2D space. However, these people overlap only on the 2D space, not in 3D. So if we are able to lift people to 3D and make our reasoning there, we should be able to avoid some of the problems, the occlusion problems that happen in the Trackin setting. So that's one of our insights and arguments here. The second one has to do with appearance. So if you look at this video and you focus at that player in the center, I have selected actually a few keyframes here. So 1, 2, 3, 4. So if you look at these bounding boxes, you can see that the appearance of each bounding box can change rapidly as the body deforms. However, what stays constant is the appearance of individual points on the 3D body of the person. So the left shoulder here is always red during the whole video. So no matter what the pose or the viewpoint of the person is here. So our argument is that if we operate in the 3D space, we can use the 3D body as a representation of the appearance, which is invariant to the viewpoint and the pose of the person. So all these points correspond to the same location on the body of the person. So we have this this property that we are effectively invariant to viewpoint and pose. Maybe if we ignore this some lighting changes or shading, the effect of shading here. So yeah, those are our two main arguments for why we would like to do our tracking in 3D. First, it has to do with the location, the 3D location being more separable than the 2D location. And second, the 3D appearance is invariant to viewpoint and pose here. So yeah, so those are our insights. And I will show how we operationalize these insights in this PHALP work. So here is an overview of a more general way of thinking of tracking. So a high-level overview of how many of these pipelines are actually working. So first, we assume we have some bounding box detections for each person in the video. Then we extract some feature representation on each bounding box. And third, there is some processing that is going on among all detections, such that we can figure out which people correspond to kind of like cluster identities together. And after this spatial temporal aggregation and update, we solve for the correct association of the people in the video and get this tracklet. Our argument here is that this feature extraction step is can be quite weak or can miss a lot of useful information. So we intervene here and we try to create kind of a richer representation for each bounding box. So instead of having maybe an arbitrary feature representation, we actually operate with 3D features. So we have this machinery to lift people to 3D. So we use it to be able to capture more 3D information in these 3 different channels. And for this lifting, we use this human mesh and appearance recovery model, which is related to what I saw earlier, this recovery model that we trained with this movie data. So here we have this human mesh recovery model that recovers the 3D pose of the person in a cropped bounding box. Then if we know the location of the bounding box on the image, we can also get an approximation or a rough estimate for the 3D location of the person in the camera space. And here we extend also this HMR human mesh recovery model by having an appearance head that gives us provides an estimate of the appearance of the person in this pose and viewpoint invariant space, this UV map, effectively. So yeah, that's what where we believe that we need to intervene to make this to capture richer information for tracking, and then you can you have this spatiotemporal aggregation step. There are different ways to do that. Before, or in Europe's last year, we proposed a transformer model that is applied on every bounding box, and effectively every bounding box across all frames, and yeah, all bounding boxes for all people across all frames attend to every other bounding box in the video, and their representations are updated accordingly. And this is reasonable, but the main limitation here is that we really need to have a lot of training data to train this model. And unfortunately, we have very few videos with fully annotated tracklets to be able to train a particularly data-hungry model like this transformer here. So instead of that, we try to rethink this pipeline for the aggregation and the prediction here. And we again go back to thinking more in the 3D space, what we have in our 3D representations. So if we have good lifting of people to 3D, it is easier to actually predict the future of this 3D tracklet. It's easier to predict how the tracklet evolves over time. So that's the insight we use here, and the main pipeline here is that, assuming you have a tracklet and you have some representation for this tracklet, I will go into more details into this soon. But assuming you have this tracklet, and you operate in the 3D space, it is easier to predict what's the next step for this tracklet, how this tracklet will look like in the next frame. So we can get this prediction, and when we actually see the frame, we are also able to reconstruct every people to 3D. And the only thing we need to do is to be able to resolve this association, to try to associate our prediction with to connect it with one of the lifted people that we have in the next frame here. So that's the idea, that prediction should be much easier if we operate in this 3D space. And indeed, we do have the toolbox to actually make this, to build these prediction models here. And we do follow the this disentanglement that we had before in 3D pose, 3D location, and 3D appearance. So we build a prediction model for each one. We use a prediction model for each one independently. So for 3D pose, this is very much what I presented earlier, what we used in this, what we trained with the movie data. So for pose first, we see the past poses for a tracklet. We have this human mesh and motion recovery model, and from that we can start predicting what's the future. We can get the motion feature and predict what's the future pose for this tracklet. So this operates on the pose space only, and we have been able to train that with the data from movies that we had that we leveraged before, and we can keep predicting in the future for a short time window. So that's the most data hungry model when it comes to prediction here for the pose. Then for the location, for the 3D location, here we mostly care about the small time window into the future. So this could be pretty simple. So what we actually use here is we make a pretty simple assumption of constant velocity in a local window, so we can estimate the future 3D location of the person using just a linear regression here. Of course, you can build more sophisticated models and actually even data-driven models here if you have the data of how people move in the 3D space. This is a design choice that we made and requires the least possible data for training. So that's about the location. And then we also have the appearance. This is also the way we build our model. This is also this also requires very little data to train. So if you remember, we do operate in this pose and viewpoint invariant space. So we can estimate the this UV map for the appearance of each person, for every person over video, over its frame. And then because this UV map provides us direct correspondence, so we know for each pixel, we know where on the body it corresponds to, then the aggregation of these feature maps, these UV maps, can actually be done just with a simple addition or with some weighted sum here, assuming that the appearance of the person remains constant over the video. So with this assumption, our prediction is just this this weighted sum of the past observations about the appearance of the person. So again, no data really involved for this step. So yeah, we are able to build these independent prediction models for its representation, and then the final step is just to solve for association, to associate detections and combine them into, or cluster them into tracklets. And for that, again, we have some distance functions, one for the appearance, one for the 3D pose, and one for the 3D location. The only thing we need to tune here is the weighting for the different functions, or for different distances, and that's the only step where we actually use these tracking datasets to tune these parameters. So just if there are only 4 or 5 parameters that will be tuned here. That's the only thing that needs to be learned from actual tracking data. So that's very very easy to optimize without having access to a lot of tracking data. And that's how our overall pipeline looks like. We start with the detections, we accumulate them slowly over each frame to tracklets. Every time we do this, we find a new detection, we aggregate the representations for pose, location, appearance, and then before we see a new frame, we make a prediction about how the person should look like, both its appearance, its location, and its 3D pose. And then after we see the frame, we try to associate our prediction with one of the detections that we have from the lifting step here. And for that, we use simple Hungarian algorithm. All right, so for some, let me go to some results here. We use this head mask visualization. I think this is easier to be able to track, to make sure that the detections are actually correct. We highlight with these red circles on which people to actually pay more attention, and these are some more challenging cases that we have highlighted. I will keep some of these videos playing, but I would be happy to also answer any questions if you may have. It's a good time to interrupt me here.
Yeah, thank you for the wonderful talk.
No, I haven't finished. Sorry, I have some more to go through. But,
yeah.
I think I will. While these results keep playing, you can. If there's any question, you can let me know, or I will conclude soon.
Great. Yeah, I do have some questions. I'll probably just ask some of them now. One is a very basic question. So this is under the paradigm of detect and track, right? You're saying for transformer, it'll input bounding boxes from multiple frames of like all the detected objects. Is that correct?
Yeah, of all detected humans. Yes.
Then there will be different numbers of bounding boxes at each frame and across different frames. So is there any position embedding, or how does transformer handle that?
Yeah, there is a position embedding for the location of the bounding box. So the sender and the scale of the bounding box, and also the time instance.
I see.
So this is provided in the input. Yeah.
So there are two different embeddings being added to that.
Yes, the spatial and the temporal one.
I see. Do you think there's any particular part of this framework that is just particularly suitable for transformer, or why didn't you use other structures like CNN or other structures?
The very convenient thing here with the transformer is that you can actually you don't need to decide the number of humans or detections at test time. You can have as many humans as you want for each frame, and then you can mask accordingly the inputs of the transformer. So that makes it convenient for this setting where you have a known number of detections at each frame.
I see. So it's a decoder structure of the transformer.
And the encoder as well.
It is. I see. Okay. Yeah. Thank you.
Can I ask a question?
Yes.
I'm just curious. So, like, can you elaborate on what you said about like masking for the transformer? So basically, you have like upper bound of the like humans in the frame, right? And then you like mask them. Am I correct? So
you have an upper bound of overall how many detections you will have in the video. So that's we train with t time steps and n people, and that's what we're constrained at training time.
And what is the bound?
Here. I'm not sure of this detail. I need to check exactly. We do go into very high number of both frames and detections per frame. I'm not sure. I'm not sure, to be honest, about the exact number of.
I was just curious. It's like 10, 20.
Much larger than that. No, because we need to like be able to track over many frames and many people as
I see.
well.
Thank you. Yeah. Thank you.
All right. So here are some more quantitative results of this PHALP approach. We try this. They said like on different. We want this to be working well on different settings. So we have this this postdoc dataset which has sports videos and the wild videos. We have MUPOTS is more simpler scenario with simpler settings. We have AVA, which is coming from movies, and across all the datasets and most of the metrics, we achieve state-of-the-art results. Particularly, we outperform many of the 2D tracking methods here. And I have some more results. Again, these are highlighting some harder cases. Before and after. The transformer and tractor, these are 2D tracking methods, which have trouble here, particularly with the occlusion. Let's see. Yeah, this is applicable. Yeah, we want this to be applicable also in very in diverse settings. So here we also apply this on the MOT data set, and we can track people pretty reliably. And just for short roadmap, I think in general the philosophy here is to try to go beyond the single human. So we have been operating a lot in this single person, single frame setting, but we want to be able to go beyond that and to reason about objects. So here the human is jumping to actually hit the ball. We want to be able to reason also about other humans, and that's where the this tracking method is going forwards, to build tracklets for all the people in the scene. We also want to reason about the rest of the environment. So there are interesting aspects also in the static world around the humans, and we want to be able to capture that down the road. And that's from the static world. And I think the other interesting, important thing here is to also be thinking about reasoning over time and predicting the future. We have an iteration of that in this tracking paper, where we try to reason about how the person how the person pose, location, appearance will update over time. We want to be able to recover this from video as well. And here is an interesting case where it's hard to predict whether there will be a spike or there will be a block here. We want to be able to recover these these behaviors from video. Yeah, and concluding, I would like to thank my collaborators, my postdoc advisors, my PhD advisors, previous mentors they had, and also the student collaborators. And with that, I would like to conclude, and I would be happy to answer any question that you might have. Thank you.
Thank you again. I'll follow up with one question. Let's see. So I always think occlusion is a particularly challenging problem, and tracking people, especially these sports videos, where we have two teams, and each team will have many people having the same uniform, almost look exactly the same, and they'll be moving around. And this is particularly challenging. I wonder if in your work there's some, say, ablation study saying that maybe the 3D pose or viewpoint wouldn't help too much, but the 3D position of the people in the 3D space might having modeled that.
Let me see. I'm not sure if I have the slide about the breakdown. Oh, I have a slide. Let me actually pull this up. Yeah, we do have an ablation about the different these different attributes, like what happens if we remove each one of these attributes here, and which is more important. In general, we observe that the position is more important than the 3D appearance, then the appearance, and then the 3D pose. So 3D pose seems to be less important when it comes to disambiguating between different people, but still it's very crucial because it is what allows us to lift these people to 3D. We first get the pose, then given the pose, we get the location, and then we get the appearance based on that. So that's kind of the breakdown here. I don't have a breakdown when it comes to more specialized scenarios. So what happens if you have a basketball team or a soccer team where the appearance remains mostly contact, or what happens in this other scenario where people are very, very close together. So I don't have a breakdown there. This is more about general post-track. This is from the post-track dataset. This is a general breakdown for this setting.
Wonderful, wonderful. What is IDs here?
This ID switches. So this is like the number that we have a tracklet in the video. How many times we switch from one tracklet? So we change the identity of that tracklet if we segment it in different identities.
Oh, I see. Okay.
Mistakes, number of mistakes effectively in the tracking here.
I see. Without location, there's the most drop.
Yes. And nearness, I mean, we have this separately. I didn't go into more details, but this is how we define the effect. You can think of this as the depth of the person in the in the camera space. So even the depth, like this, what we consider as 3D information, is important. So that's to highlight that it's not just to the location of the pixel space. Even the depth, or like this nearness term, is important here.
Mm-hmm. Yeah, sounds good. Yeah, thank you.
Mm-hmm.
Yeah, we're at 1 o'clock, but if other people have questions, please feel free.
Mm-hmm.
Yeah, perhaps people could also email Professor Dr. Pavlakos afterwards.
Yes, doctor. Yeah. Happy to answer also questions offline if there is any. Yeah, or you can reach over email.
Yeah, there are also a bunch of one-to-one meetings after this. I think
Yeah.
3 of the attendees are going to meet you. I think that's what was the latest. So yeah, maybe they could ask you during the one-to-one meetings and have a deeper discussion.
Yeah, definitely.
Okay, we'll probably just end here, and thank you again for coming here.
Sounds good.
Okay. Yeah, everyone, we can mute ourselves.
Okay. Thank you.